right? So hello everyone. uh, Usually I like to prove things and not disprove things, because I mean I think that what has been given to us is correct most of the time. Sometimes, yeah, sometimes it is incorrect. So here I have such a case. So this formula, right? This formula is for the number of spectral lines when you go from some capital N, right? You start from a level N, and then you take all the possible transitions you can have while going to the ground state. So you could have capital N to 1, that's a transition. You could have capital N to 2, and so on. You could have capital N to capital N minus 1, that's a transition. You could also have capital N minus 1 to 1 and capital N minus 2 to 2, and so on. So capital N minus 2 to capital N minus 3. And yeah, just keep on going like that. So the first section, it contains n minus 1 transitions. The next one will contain n minus 2 transitions, and the next one will contain n minus 3 transition, and so on. So eventually you will get 1, right? So this whole sum, this can be written as n minus 1 times n upon 2 using the AP formula, right? Yeah, and that's how this formula comes to be. Now, it's good and all. This is really useful for a lot of cases, but there is a problem with this, because in this derivation, what we assumed is that none of these two transitions, those are the same energy, right? So think about it. What would happen if two of these transitions, I don't know, any of these two transitions, right? If somehow they were of the same energy, then yeah, this formula wouldn't work because it would be overcounting the stuff, right? You are counting the same energy two times. That's not right. Number of transitions, yes, it's n minus 1 times n upon 2. But number of spectral lines, it's not that, it's less than that, right? So how can we guarantee that we don't fall into that trap? How can we guarantee that we don't overcount the thing? And that's what this video is about. So this is good and all, but we need to be sure that uh, we know till when this formula works. That is, for what number of cases this formula actually works. And when it stops working, you have to be sure when that happens, right? So you might try to solve this equation. So the equation is basically just 1 upon m square minus 1 upon n square is equal to 1 upon a square minus 1 upon b square, where mn and ab are integers, right? And you might try to solve this thing and everything. Yes, it's good, you can do that, right? I won't stop you, but let's be more practical here, because we will only be caring about small capital N values, right? We won't be going till thousands or hundreds of capital N value, right? So we only need to know till what, right? So till how big should capital N be such that we start to get faults in this thing, right? And to do that, we don't need to solve this equation. Instead, we can just write a Python program and then run it, and it will tell us when you get the first fault. And once you know that, just be sure that whenever you use this formula, your capital N be less than that value, and then you can use this without having a care in the world. That makes sense, right? So that's what we are going to do today. Yeah, so let's minimize this. Okay, and okay, wait a second. All right, wait a second, and then there we go. That's Python, right? Yeah, so you can see the program over here. So I'm using this fractions module because when I want to equate, so I want to check whether two numbers are equal. I don't want to check them using the decimal notation, because the problem is sometimes two number might have similar decimal representation, but they are actually different numbers. Because yeah, and also all the numbers that we'll be calculating are all rational numbers, so it makes sense to use fractions instead of decimals, right? So we are using fractions for this thing. We are defining a function that basically gives, right, this thing. So this left hand side, we are treating this thing as a function, right, of m and n. So you put in m and n values, you will get the reduced representation, so the rational representation of whatever the value is. Cool. And I've made a list faults, okay, and I've also made a dictionary firsts. Right, so this dictionary will store all of the first cases when you achieve an energy, right? So you got some transition, you got the energy of that transition. When does that energy come the first time, right? So for which first transition does that happen? Those cases will be in the first right, this dictionary, okay. And I have this list of faults. So yeah, like for every capital N value, where does the fault happen and when does the fault happen? So when, basically that means for what N value, and where, that means what transition, right? Okay. And then you have this whole thing. You don't need to read all that, right? Yeah, okay, just going to run this thing. So it will take some time, and we are taking all the N values from 1 to 40. So yeah, it will take some time because 40 numbers it has to generate. Okay, there we go. It's doing the thing. Oh, just don't hang right now. Okay, please work, please work. Of course it works. I just thought it might hang, but no, not today. Okay, so let's see. So it finished check. Yeah, it checked 1, 2, 3, so on, and throughout these numbers it didn't even get a fault, right? So it works good and all till 35th, and the 36th N value, that's the first time you will get a fault. Right, and the fault is this thing. So you got the transition from 35 to 7, so N is 36, that's when you get the fault, and your transition is 35 to 7, right? So 35 to 7. Okay, I think we should move this a little. Right, so a transition is 35. It is all that. Okay, this is where the fault happens, and the first time this energy actually came was 7 to 5. So 7 to 5 transition, this energy is the same thing as this energy. Yeah, and does this actually work? Because it's a program, it might not work sometimes. Let's check this by hand. So you got 1 upon 5 square, which is 1 upon 25, minus 1 upon 7 square, it's like 1 upon 49. Cool. And that is equal to 1 upon 7 square, which is 1 upon 49 once again, minus, oh, you know what? Let's take 7 square out. So it will just be 1 upon 7 squared. And that times 1 minus 1 upon 5 square, so 1 minus 25. Cool. And let's actually multiply by 7 square because that will get rid of this thing. So 49 upon 25 minus 1 is equal to 1 minus 1 upon 25. So that's like 2 is equal to 49 upon 25 plus 1 upon 25. Is that correct? Actually, yeah, because like 50 upon 25, that is 2. So of course it is correct, right? And then just backtrack the thing and you will see that this actually does work, right? Or you could just, figure out the LHS and RHS value. It does work. So what that means is that we actually have a fault in our formula, that it doesn't work all the time. You can't use this formula for cases that go out to infinity. And of course you won't have to, because nobody is going to ask you for such big capital N values. They will ask you for, I don't know, 20, 18, something like that, right? They won't ask you for 36. Yeah, they won't. That's the thing. And if they do ask you, just, ignore the fact that their formula is wrong and use it blindly. I know, that doesn't look good, but trust me, these people, they don't understand what is real and what is not. So just use it because you want to make them happy, right? In reality, you should be knowing that actually doesn't work like this. And if you eventually do get a question where you can see that the guy who's asking the question does know this fact that it doesn't work all the time, then yeah, you would be having knowledge already about when it doesn't work. So cool. And that's all I wanted to say. And yeah, so you got till 40. You can run this program for more numbers and you will figure out all kinds of faults. And yeah, that's it. That's all I want to say. So this is it. See you guys in the next video. Bye.